Let's look at the ideal transformers. The transformers are used very widely in the power system, and they are used to step up the voltage and the power station, and then step down the voltage and the load. So you transform the power at a higher voltage, which means the lower current, and so you're gonna for the same amount of power, and so you're gonna reduce the power losses due to the I square R losses, right, on the transmission lines. But the transformers are a little bit more complicated to analyze. So we start with the ideal transformer. So this is a prime, and there are going to be more detailed analysis when you take 320. Some of you might do that. And so the assumption for ideal transformer, there are four assumptions. The first one is no leakage flux. That means the perfect coupling all these flux linking the first winding going to be linking the second winding, or primary winding or secondary winding. And two is the infinite permeability. The magnetic core with the transformer is perfect magnetic conductive. That means the permeability mu is infinity, and then we have zero winding losses, no resistance, and also zero core losses. And we're not counting core losses in these ideal transformers. Let's look at the voltage ratios and current ratios. Let's start with looking at the voltage ratios. And we always assume on this one side, the primary side, we have N1 turns, and then we have N2 turns, right? I will assume all the drawings here like that. And since we don't have any leakage, that means all the flux linking, the first one is gonna be linking the second one. So this is the drawing for this one. And if you look at the dot terminal, you put dots here, you should put dots here, right? Because these two, if you have current going into both terminals, you will have the flux add together. So that's how the symbol for the ideal transformer. For ideal transformer, we normally put two straight lines to indicate this has a magnetic core. Okay, and based on Faraday's law, we have V1 is going to be equal N1 times d phi dt, and we have V2 is equal N2 d phi dt. So therefore, the ratio for this one is V1 over V2 is equal N1 over N2. Very simple, right? And if we look at the different arrangement for the second winding, so here I have a dotted terminal, then dotted terminal now is moved to the downside, and this one here, the induced voltage V1 is still equal N1 times d phi dt, and for the second winding now, V2 is equal negative N2 d phi dt. And I explain this in more detail about Faraday's law in the Google Colab notes. Check out that if you don't understand why we should have a negative sign for the V2. Okay, basically the Faraday's law always trying to induce a voltage that tends to produce a current that will oppose the change of the flux if that circuit is closed. Right. So the ratio V1 V2 is going to be equal negative N1 over N2 for this one. But if you want to sort of do the shortcut of this, and if you compare these two cases, and this V1 is from the dotted to undotted, and labeled this V2 is also from dotted to undotted, so that's where you don't have a negative sign. But for this one here, for second case, when you need the negative sign, is that one end the voltage is from dotted to undotted, and the other side is from undotted to dotted, right? So that's the difference. And let's look at the current ratio. In the current ratio here, I think the text had a fundamental mistake here, or error there. The derivation is completely wrong. I'm not following the text. So this is the correct derivation. So we need the assumption of the permeability for the core is infinity. The text uses the losses is 0. I don't think that's correct. I mean, if even the losses like ideal inductors has 0 loss, but you don't have instantaneous power is 0, right? You can still have instantaneous power going back and forth because the inductor can store energy. But in any case, so I'm using the permeability mu is equal to infinity, that assumption for the ideal transformer. And let's look at the first case. Again, here we put the dotted terminal, this dotted terminal, and these two fluxes, and definitely add up to each other. So the total flux y sub 2 1 plus phi sub 1 2, that's equal k times n1 times I1 plus k times n2 times I2. So the k now is not a common coefficient anymore. The k is a constant related to the magnetic core material and also geometry of the magnetic core. Right? But for if the mu is equal infinity, and that will cause k equal to infinity. And in ECE 320, you're gonna learn the k is inverse reluctance. So if the permeability is infinity, that means reluctance is 0. So the inverse of that reluctance is infinity again. And based on that, we have N1. I'm using the same k because these two flux, they have the same path. So therefore, that constant of the reluctance is the same. And so therefore, we have N1 I1 plus N2 times I2 is going to be equal phi 1 2 plus phi 2 1 over k. And the flux, they are finite, right? So the k is infinite, so therefore you get a 0. So that's how you get the N1 I1 over I2. I1 over I2 is equal negative N2 over N1. So that's for the current ratio for this case. And if we do the similar, the derivation for the this current here, for this case, and the current now, the flux, they are actually opposite to each other, right? So the dotted terminal here and dotted terminal here, and so therefore the current I2 actually has the flux going in the opposite direction. So the total flux, let's say the net flux I phi 1 2 phi 2 1 minus phi 1 2 is going to be equal k times n1 I1, because the phi 2 1 is caused by n1 by the first winding, and then minus k times I2 n2 times I2. Let me write this. And the same k is infinite because the permeability phi is infinity. So we have n1 minus I1, n1 times I1 minus n2 times I2 is going to be equal to 0. That's 0 because that's phi 1 2 minus phi 2 1 divided by the k, that's equal to 0, right? So therefore, for this one here, the current ratio is n I1 over I2 is equal to N2 over N1. So there are no negative sign for this, right? So because these two flux components, they are opposite to each other, and they should be 0 because the permeability. And if that's why you move to the other side, you don't have a negative sign, right? But the current always be proportional to the current ratio, always be proportional to the inverse of the turns ratio, right? So that's the current ratio and the voltage ratio. And next we're gonna look at the impedance, the equivalent impedance. Okay.